Hello, I'm Nicholas Narzinsky, and I'll be presenting a video on imperfections in solids. So what are imperfections in solids and why do they occur? Imperfections occur from deviations in arrangement of its particles and occur naturally for a multitude of reasons. Could be they're mixed with impurities, they crystallize irregularly or too fast, and or stress or deformation causes these different defects. So among these types of imperfections, there's three types. There's point defects, line defects, and area defects. Point defects are deviations in arrangement of particles and impurities. And among point defects, there are three types: vacancy atoms, interstitial atoms, and substitutional atoms. Line defects are lines along rows of atoms where atoms are arranged anomalously, causing certain deformations and dislocations. Among them, there are two types, edge dislocation and screw dislocation. And lastly, we have area defects, in which there are large discontinuities in lattice, usually encompassing a large area. And among it, we only have one type, being grain boundaries. So first, we'll be talking about vacancy atoms. So much like substitutional and interstitial atoms, there are point defects, in which vacant lattice sites occur where there should be or would be an atom, and occur naturally in all crystalline materials. And these vacant sites can cause distortion of planes and has a couple of effects on material properties, which we'll get into later. So next we'll be talking about substitutional and interstitial atoms or solutions. And we call them solutions because it's a mix of two different particles. So substitutional solutions are when solute atoms replace solvent atoms. And solute atoms must be large enough to replace the lattice sites of the solvent atoms, and usually they can be a bit smaller or bigger, and depending on whether they're smaller or bigger will cause different deformations. And because they're in similar size, they're usually in proximity on the periodic table. For example, like copper and nickel, or zinc and aluminum, could be either or. So interstitial solutions are when solute atoms inject themselves between solvent atoms, or in the spaces between solvent atoms. Solute atoms must be small enough in order to fit between the solvent atoms and between those spaces and enter, interstitially. Atomic size should be about 40% the size of the solvent atoms, in order to fit in between those crevices, and tend to be carbon, hydrogen, oxygen, and nitrogen. I say this because carbon, hydrogen, oxygen, and nitrogen are all relatively small atoms and are also very abundant, so they usually make their way in between solvent atoms. So next we'll be getting into my 3D model. So here we have a substitutional solution in which these blue spheres represent metal solvent, and these orange spheres represent solute atoms. You could imagine that while this lattice forms, solute rushes in into these lattice sites, replacing solvent atoms, or they simply just substitute for them. And even though this model doesn't show deformation, since this substitutional atom is smaller, you could imagine that the solvent atoms would sort of distort inward, like a plane would go inward would occur. And this model could also represent vacancy atoms if we just substituted, or I guess deleted, these orange spheres which represent the solute atoms. And again, similar deformations would occur where sort of plane inward would happen. So next we have an interstitial solid solution, in which again these blue spheres represent a solvent atom, and the tiny orange spheres in between these spaces represent a solute. So while this lattice forms, these atoms sort of get stuck or rush in to these spaces, between these atoms. Um, and unlike substitutional atoms, these interstitial atoms don't really cause deformation, but still will affect material properties, in which we'll get into later on. So next I want to talk about line defects, in which we have two types of linear dislocation known as edge and screw dislocation. So again, line defects are one-dimensional defects that produce a dislocation line. The difference is how the dislocation line affects lattice and what sort of deformation happens. Edge dislocation produces a wave-like deformation from planes of atom being inserted perpendicular to the dislocation line, whereas screw dislocation produces a staircase-like formation because plane of atoms is being inserted parallel to dislocation line. So you could imagine with the screw dislocation that we sort of have a perfect solid block in which we then insert a plane of atoms kind of at the top of a block in which a new stair sort of begins to form. Whereas an edge dislocation, sort of imagine a plane of atoms being inserted at the side of a block and an expansion-like effect happens. So lastly, we'll talk about an area defect being grain boundaries. So a grain boundary is a region, a space between crystals that occur when atoms are not exactly aligned with either side of a grain. And a grain being where it's a plane where two lattice structures meet. And that defect occurs when those two lattice structures meet and the orientation differs because, again, those atoms are not exactly aligned with either side of the grain. And usually on each side of the grain, there are same structure and chemical properties on each side of the boundary, just the orientation differs. But this can also occur between two different crystallites of different properties. So how do these defects affect material properties? Point defects greatly affect material properties and often determine most material properties. This is in part because of impurities, like and we get into weight and atom percent, but also vacancies and substitutional atoms causing different deformations. So they can affect conductivity, mechanical strength, malleability, and conductivity. So vacancies and substitutional atoms can affect electron and heat flow, making it sort of like a boundary where electron and heat can't pass through. Whereas interstitial atoms, since it's an impurity, kind of they mix properties of the impurity with the solvent, causing those to mix and changing up the properties a little bit to get a little bit of the impurity and the solvent. So next, line defects, which they're essential for controlling deformation-like properties. And these properties include malleability, breakage of bronze, strength, and whatnot. So these dislocations can cause lattice structures to weaken and make elements more malleable, more brittle, and give them less strength. And lastly, we have area defects, in which they mainly control thermal and electrical conduction. The larger and greater number of grain boundaries decrease thermal and electrical conductivity. You can imagine that these boundaries act as roadblocks, much like the vacancies and substitutional atoms kind of disrupt heat flow. These boundaries will again disrupt heat flow and electron flow. So in conclusion, we covered all the imperfections in solids, in which there are three types: point defects, line defects, and area defects. Among point defects, we covered vacancy, interstitial, and substitutional atoms. And we stated that they were defects in arrangement of particles and impurities, in which they had the greatest effect on most material properties. Line defects, we had two types: edge and screw dislocation, in which they were defects in rows of atoms where lines of dislocation would occur. And because of these dislocations, they would mostly have effects on properties like strength and malleability, and other properties of deformation. And lastly, we covered area defects, in which there's only one type, being grain boundaries. And they were defects in orientation between lattice structure and greatly affect thermal and electrical conductivity. So let me know if you have any questions, and thank you for watching.